Alright, in this video we're going to be looking at generating PWM, which is short for pulse width modulation. So, like we saw in the last video, we've got our microcontroller, we've got a physical pin on it, and we're generating a waveform out of that pin. Right, so that's what we're interested in. But let's have a look at what PWM actually is. So, if I have a waveform, so this is time, this is voltage, and these lines represent periods of equal time. PWM would look something a little bit like this. Now remember, when we generate a square wave, the amount of time that the pulse is high versus the amount of time that the pulse is low was equal. Whereas in PWM, what we're actually interested in doing is modifying what is known as the mark-space ratio. So this would be the mark, and this would be known as the space. Well, basically the amount of time that it is on versus the pulse is off. And by doing that, we can actually control the average DC voltage associated on that pin. So by changing the duty cycle, in other words the width of that pulse, while keeping the period the same between them, so we have fixed frequency but variable duty cycle, so which goes from 0 to 100%, we can control the average voltage on that pin, on this guy here. And that's quite a useful thing to be able to do. So we're effectively going from digital to analog in a very rough way. We can do many more things that are more advanced with PWM, like creating sine waves and other types of waves, but generally, especially with respect to motor control, or brightness of a lamp, for example, this is what we're trying to do. So let's have a look at how affecting the mark-space ratio, or that duty cycle, changes the average voltage. So same thing again, voltage versus time with equal periods. Here's another waveform. And in this case, this is our on time. That's the on time and that's the off time. So let's say that's 90% on versus 10% off. Of course, those will always add up to 100%. If VIO equals 5 volts, then VDC, so where VIO is the normal output voltage if it was just a digital pin, would be equal to VIO times the duty cycle, which in this case would give us 4.5 volts. Right, let's see that again. Voltage versus time, equal spacing, fixed frequency, remember, where we were on for 50% of the time and off for 50% of the time. Remembering that DC is nothing more than the average voltage. So in this case we would get 50% up here, 50% down here, so 5 volts times 50% equals 2.5 volts. So we're effectively controlling that average voltage. 50% of the time it's on, 50% of the time it's off. Therefore we have half the maximum voltage for this. Right, so that's how you can control the voltage using PWM. But how do we get our timer to generate PWM? Well, what we can do is, remember, our timer is doing something like this, counting up and then resetting itself back down again. Now we're not using CTC mode. Okay, so time versus time account value, and not CTC. That's quite important. We have a top value, but we also have an OCR value. Now, this is how it works. On our pin, time versus voltage, we have a number of modes that we can operate in. We can operate in clear, so this mode here, clear, OCNA, so that's that pin. So remember, OCNA is this pin here, OCNA, for example, or B or C. We've got 3 channels. On compare match, so that's a compare match between OCR value and the time account value, set on top, or we can set on compare match and clear on top. So the only difference between these two is inverting the way it works. So let's have a look what this would do on our pin. So if we were to go, for example, to clear on compare match, let's go set on compare match, clear on top, so we're going to be using this mode. What will happen is that we'll start off on a compare match, we'll come up, and on a top we will clear on top, set on compare match. So we'll come down again on a top value. Right, and we'll get something that looks like that. So each of those compare events, these bits right here, will cause the output voltage to go up, and every time our timer reaches the top value, which is this bit, it will be cleared again. Now, because the period here is the same every time, it means that the frequency of our output signal is fixed. Right? We're not changing the top value that the timer is counting up to. That part is fixed, and therefore the frequency is fixed. However, what we can do is move the OCR value up and down. So, for example, if I was to move it down here, okay, so there's 2 and there's 1. We'll draw this one. We'll draw that one in blue just to make it a little bit different. Right? You'll see that we would start our pulse much earlier, and therefore the duty cycle would be on for much longer. We would have a higher duty cycle for this corresponding output. So once again, timer counter is set up in a PWM mode. This is fast PWM by the way, so that means we have only a single slope. This is the easiest to use, so I do encourage you to use it. It counts up to a top value, which we're going to set up later. When it does, it resets back to 0, and it just repeats endlessly. We also set up an OCR value, just like we did in CTC mode, except rather than affecting the frequency, this time it actually affects the duty cycle. So the higher we make our CTC mode, the higher our OCR value, depending whether we're operating in set or clear on match. Alright, so there's 2 different modes, they're going to have opposite effects. If we're operating on the set on compare match, the higher the OCR value, so set on compare, the higher the OCR value, the lower the duty cycle, and therefore the lower the DC voltage. Correspondingly, if we clear on compare match, the higher the OCR value, the larger the duty cycle, and the larger the average voltage on the output pin. Right, so these ones are just opposite effect, and it just comes down to preference, which way round you want to be able to send it. Alright, larger value gives you a larger duty cycle, or a larger value gives you a lower duty cycle. It's just a matter of preference. Right, but they both do the same thing effectively, being able to manipulate how long, well, when the output pin voltage goes high, therefore how long it stays on before it is cleared at the top value or set, depending on the mode that you're using. Alright, so that's basically PWM. Right, remembering we have fixed frequency but variable duty cycle to control the average voltage on our pin. So let's look at how we would actually set this up. Once again, we have TCC-R1A as one of our timer counter control registers, and the first 6 bits set up the compare mode for Fast PWM. Noting we have a different table that we're using from CTC mode. Let's say we're actually only interested in channel A, so those middle 4 bits we can ignore, and so we can say TCC-R1A is equal to in binary. Once again, based on your preference, let's say we're interested in set on compare match clear at top, so 1 1 comes in here, 0 0 0 0, so we're not interested in that, and then we come to our 2 waveform generation bits. Now, just like we did in CTC mode, we have quite a number of modes that our timer can operate in. In terms of Fast PWM, which like I said is the easiest to use, we've got 1 2 3 4 5 different modes that will give us Fast PWM. The difference between these is the top value. These 3 have a fixed top value, okay, whether you want 8-bit, 9-bit or 10-bit. Now that only affects the frequency of which your PWM generation is at. It also affects the resolution, which is how accurate or the smallest changes you can make to the duty cycle. The larger that number there, then the more precise your accuracy can be. But it also affects, the frequency. So as we see here, the PWM frequency for the output can be calculated from this formula. So that's the output frequency, and there we see that top value. So top value changes the output frequency and the output resolution. And we want normally a higher resolution. Higher resolution, more accurate PWM, because we can control the duty cycle in much finer steps. Right, the other 2 modes we have are the ICRN and the OCRNA registers can be used as the top value. Now I've told a few of you previously that ICRN is probably not a good idea. I take that back, it is actually alright, and you can use this mode if not using input capture. So if you're not using the input capture on this timer, then feel free to use ICRN as the top value. It's generally only recommended if you are using a fixed PWM frequency. If you're going to be modifying it a lot, it's much better to use OCRNA and then use one of the channels B or C to be able to control the corresponding duty cycle. Alright, so if you've got a fixed frequency, fixed F, then use ICRN, or if one of these other modes up here, 8-bit, 9-bit or 10-bit, does what you need, you're not too fussed about the actual frequency, you don't need a critical value, and the resolution is good enough within these, then by all means use those. However, if you want a particular frequency or particular resolution higher than you would get with the 10-bit here, then you can use one of these 2 down here. Alright, so if you've got a fixed frequency, ICRN is alright, or if you've got a variable frequency, then we'd normally use the OCRNA as the top value. One thing to be aware of is that if you are using OCRNA as the top value, then we can't also use it to set the duty cycle associated with our channel A output. Right? It won't do both. You'll end up not generating PWM if you do that. So for us, I'm going to use an example where we have, let's say we want to generate at 25 kilohertz. Now if we were to substitute these values in, 8, 9 or 10-bit, we'd find that we wouldn't get with the prescalers exactly that frequency. So the way we're going to get around that is by using this mode 14, where we use the ICRN value as our top value. If we come back to TCCR1A, we see we're setting 1 1 and 1 0, which are these 2 here. and the corresponding value should be 10 into TCCR1A. So 10, and remember, I like to tick these off as I go to remember that we've done them. Coming down to TCCR1B, we're not using input capture, so we can get rid of those. We can set this register up, TCCR1B equals in binary 0, 0, 0, WGM 1, 3 and 1, 2. In this case, those are those guys there, both equal to 1. So 1, 1, and then the lower 3 bits are the clock select bits, which set up our prescaler. So to select those, we need to come and we need to solve this equation here. So in my example, I want 25k is equal to 86 over n times 1 plus top. So once again, just like we have in CTC mode, we've got two variables to play with: the prescaler, which are these values here, and the top value, which in this case is ICRN, or for us ICR1A. Right, so we have two variables. Like I say, it's normally easier to play with the prescalers first, because you've got a fixed number of those before you start playing with the top values. In this case, we're going to use 8. So we're going to have 86 divided by 8 times 1 plus 40, sorry, 1 plus 39. And if you work that one out, we should get to 25,000. So once again, we've managed to set a particular frequency we want by using ICRN, or ICR1A for this, and a prescaler of 8. So therefore our clock select bits will be 0, 1, 0. Alright, there's our setup complete. So in summary, TCCR1A is equal to, now we could use those masks that I showed you in earlier videos. So in this case it would be 1 shifted along COM1A1 board with 1 shifted along COM1A0 board with 1 shifted along WGM11. And I do recommend that you do use these masks when you set these registers. TCCR1B is equal to the corresponding bits here, so we will have WGM13, 1, 2, WGM12, and ORed with that clock select bit, which will be CS11. We also need to set up our ICR1 register. Pretty sure it's ICR1 and not ICRA. Yep, that would be correct. Is equal to 39. And our OCR1A will be equal to whatever we want our duty cycle to be, where that value can go between 0 to 39. So the resolution that we have in this particular example is actually very low, which may not suit our application, but it might be good enough. So we have 40 discrete steps for our duty cycle at the particular frequency, and of course DDR B equal to whatever it is to make our OCNA pin out and output. Alright, so that's PWM. You'll see in this particular example what we've done is use timer 1 to generate fast PWM from the OC1A pin here. We've had a look at how PWM is generated by varying the mark-space ratio, also known as the duty cycle. We've used PWM with a fixed frequency but a variable duty cycle. You can get variable frequency with variable duty cycle, but I recommend if you're doing something like that, then you have a look at the phase and frequency correct PWM modes. We've had a look how PWM actually works in terms of the average voltage. We've seen voltage on versus voltage off, calculated the average, and therefore had a look how the voltage can change. And we've looked how the timer actually works to be able to generate that. We've set up the registers, and we've seen how we can vary the top value using ICRN if we have a fixed frequency that we want to be able to get exact frequency, or we can do it using OCRNA for variable frequency or fixed ones if we have these fixed values here. And completing the timing calculations, we've come up with the registers that set this up. The only problem that I would find with this particular example is we only have 40 discrete steps from 0 to 100% duty cycle, which I would think is a little low, but perhaps that would be fine for your particular application. If not, we can come back to this equation, try and find a larger value for top, anything up to 2 to the power 16 minus 1, and change the prescaler accordingly.